Richard James will present to you Decimal Tutorial 3, Part B. Yes, this is another opportunity to show off a bit of mathematics. Here we have only multiplication. We therefore do not expect any rocket science. We may solve the problem multiplying from left to right. For example, 4.2 times 10 to the power of 4, then multiply the result by 5 and finish up multiplying by 10 to the power of negative 3. Beginning from left to right, we have 4.2 that we multiply by 10 to the power of 4, then we multiply by 5, then we finish up by multiplying that result by 10 to the power of negative 3. 4.2 multiplied by 5 is equal to 21. And when we multiply numbers that have the same base, we add the indices. The indices are 4 and negative 3. We therefore add 10 and negative 3, and the result is equal to 1. Different signs. Subtract the smaller from the larger, and the answer will have the same sign as the larger. Of course, we are multiplying 10 to the power of 4 by 10 to the power of 3. Therefore, we do not expect any difficulty, seeing that our answer should be 210, because we have 4.2 multiplied by 5 is equal to 21. And we will see on a subsequent slide why we can just multiply 4.2 by 5 and the result is 21. We have no difficulty seeing that very quickly. So here we have the result of rearranging the initial problem statement, putting, as we call them, the flat numbers together, and the powers of 10. There we have them together. So the result will be then 21, which is the result of multiplying 4.2 by 5 is 21, and also multiplying those numbers, same base, we add the indices, we have 10 to the power of 1. 10 to the power of 1 is equal to 10. As we know, any number that is raised to the power of 1 is equal to that same number. So 10 to the power of 1 is equal to 10. And the baby that has not yet been born can multiply a whole number by 10. It's as easy as including a trailing 0. Now for mathematics. We will take a look at a little mathematics. Finish up by writing the answer in standard form. Not quite yet. We will finish up everything that has to do with that same problem. Then we will move to the mathematics in order that when we get there, we do not have to return to that same problem. The number needs to have one non-zero digit to the left of the decimal point. Count the number of places by which the number has to be increased or decreased. So that number in standard form, or any number in standard form, will have only one non-zero digit to the left of the decimal point. Why do we start there? We start there because a whole number is considered to have its point at the extreme right. The number is decreased by 2 places of decimal. The number is therefore divided by 10 to the power of 2, or the equivalent is 100. And how do we know that we have a reduction? Because we have all of 210 here. All we have here is 2.10. Therefore, there is a reduction. And we realize because of the location of the point in this number relative to the location of the point, or the assumed location of the point in the previous number, that there is a reduction by 2 places of decimal. And that is equivalent to, if we are going from here to here, dividing by 100 or 10 to the power of 2. But we cannot do that and be right unless we are prepared to make an adjustment. We need to recover the original value of the number by multiplying by 100 or multiplying by 10 to the power of 2. So here we have divided by 10 to the power of 2. To recover the original value, we will multiply by 10 to the power of 2. A number that initially had non-zero digits to the left of the decimal point is called a large number and will be accompanied by a positive power of 10 in the end. Here we go. We did not show you how to multiply 4.2 by 5 just yet, because there is an easy way to multiply by 5, as long as it is very easy to find half of the multiplicand. Let us take a number and multiply by 5. 4.2, which is the one that we have in the statement of this problem. 4.2 multiplied by 5. 5 is a half of 10, or we may say that 5 is equal to 10 over 2. Let us replace the 5 with 10 over 2. So instead of 5, we write 10 over 2. The fraction may be reduced by a common factor of 2. 2 divided by 2 is, divide 2 by 2, the result is 1. And divide 4.2 by 2, the result is 21. All we need to do is increase the result by 1 place of decimal, which is the same as multiplying by 10. And we know who can do that already. So we know who can multiply by 10, which is the same as increasing a number by 1 place of decimal. So this 21 that we have right here, we will increase by 1 place of decimal, which is the same as multiplying by 10. 21. It is as easy as that. Therefore, if we need to multiply a number by 5, we quickly take half of the number and increase the answer by 1 place of decimal. So let's go with 816. Let us multiply this by 5. What do? Quickly take half of the number. Half of 8 is 4, and half of 16 is 8. Quickly take half of the number. We say a half of 8 is 4, and we say a half of 16 is 8. But do not forget the 0 that would have been the result of attempting to divide 1 by 2. So we really need to say 8 divided by 2 is equal to 4. Then we say 2 into 1, 0, and then 2 into 16 is 8. So we will actually have 408, and all we need to do is increase that by 1 place of decimal, or just multiply by 10 by including a 0 in the end, and that's all there is to it. Here we have another one. Take half of the number, which is 472. A half of 4 is 2, and a half of 72 is 36. And all we need to do is multiply by 10 or increase by 1 place of decimal, and that is the answer. So it is as easy as that if we are multiplying by 5. Now we have another number, 1052. Take half of the number. A half of 10 is 5, and a half of 52 is 26. And then what do? Multiply by 10 by including another 0, or we may say increase by 1 place of decimal. Well, we are just opting to say multiply by 10, which is including a trailing 0, rather than increase by 1 place of decimal. When we have decimals, then we will say increase by 1 place of decimal. A half of 225 is equal to 112.5. We may divide the number from left to right, and when we encounter the 5, we say a half of 5 is 2.5. Or we may say a half of 25 is 12.5. Either way, the half of 225 is not difficult to arrive at. There we have it. And what do? Multiplying by 10 and increasing by 1 place of decimal are the same thing. However, because of the form of the answer, it is more convenient to say increase by 1 place of decimal. So that is your answer. There we have another one that has a decimal fraction part to it. That number may easily be divided by 2. Divide each of 4, 12, and 6 by 2. So 4 divided by 2 is 2. Then we say into 1. We can, so we put a 0 and then say 2 into 12 is 6, and 2 into 6 is 3. So there we have 2.063. All we need to do is increase the answer by 1 place of decimal, and that is all there is to it. That is how we multiply very quickly by 5. Previously, we made use of the relationship between 4 and 25. Now, we are making use of the relationship between 2 and 5. In the same way, 8 is related to 125, and 16 is related to 625. This one is for the candidates who have calculator myelitis, which is the new disease in schools these days. Calculator myelitis. 402 is a multiple of 67, and 67 is a prime number, and we are dividing by a number that is related to 71. So not quite 71, but a number that is related to 71. And of course, 71 is a prime number, which is the number that 0.71 is related to. Surely we would have an infinite decimal. For this one, we will make use of the result that we obtain from our calculator. surely we could proceed without the use of the calculator, as we have done on occasions or on previous occasions. But we do not need this particular problem to prove our point. We have done that on previous occasions already, that is, dividing decimals without the use of a calculator. Besides, the figure obtained is not to be supplied as a part of the answer. Only the approximations and standard form are required. We will now write the answer correct to 2 decimal places. Locate the second decimal place 2 digits to the right of the decimal point. 2 digits to the right of the decimal point. That is where we will locate 2 places of decimal. Right there we begin. Notice that when we are counting the number of decimal places, we start at the first decimal place, whether or not it is equal to 0. So we begin at the first decimal place, and we are beginning there, whether or not it is equal to 0. If we were counting significant figures, we do not begin counting significant figures until we encounter the first non-zero digit. But if we are counting decimal places, we begin at the first decimal place, whether or not it is equal to 0. So there is our first one, and that is the second one. Locate the second decimal place 2 digits to the right of the decimal point. Then we check the digit that is next in order of significance, the one to the right of that digit. That digit is a 6, which meets the requirement to be greater than or equal to 5 in order that we may add 1 to the digit in question. So we will add 1 to the digit in question. 5 plus 1 is equal to 6. The other digits are not affected and return as they are. So our answer is 0.06. When rounding numbers, if the digit next in order of significance to the digit in question is greater than or equal to 5, then 1 is added to the digit in question. In this particular case, the digit in question is the one in the second decimal place. So this is the digit in question, the one in the second decimal place, because we are writing the number correct to 2 decimal places, and the one next in order of significance to it is greater than or equal to 5, so we add 1 to the digit in question. We may write the answer correct to 2 significant figures. Locate the second digit in order of significance by counting from the left most significant digit. So the most significant digit in this case is this 5, which is the first non-zero digit that we encounter. Right there. So we are counting from the first non-zero digit, which is the first significant digit. Check the digit that is next in order of significance, the one located to the right. The other digits to the left are not affected and return as they are. When rounding numbers, if the digit next in order of significance to the digit in question is greater than or equal to 5, then we add 1 to the digit in question. In this particular case, the digit in question is the second significant figure, or the second most significant digit. So we start here. 1, 2. The one next in order of significance is 6. Because it is greater than 5, if it were equal to 5, we would have done the same thing. Because it is greater than 5, we add 1 to this one. That gives us 7. Because this is greater than or equal to 5, we add 1 to this one. That's equal to 7. And the other digits return as they are. We will write the answer obtained on the previous slide in standard form. When writing a number in standard form, the number is written in such a way that there is only one non-zero digit in front of or to the left of the decimal point. So there is our number. Count the number of decimal places that will represent the difference between the original number and the number written in standard form. So we start there. 1, 2. There is where we have to focus, because we have the standard form number to be written and we need only one non-zero digit to the left of the decimal point. The number is increased by 2 decimal places. The number is therefore multiplied by 100, or 10 to the power of 2. Whereas we have 0 point something, now we have 5 point something. This number is obviously smaller than this. Therefore, in order to arrive from here to here, it means that we would have done somewhat of an increase. And the increase is related to the number of decimal places that differentiates this number from this one. And the number of decimal places will be 2 decimal places. So if we have the difference between these two is by 2 places of decimal, and this represents an increase, so this represents an increase over this one by 2 places of decimal. We need to return this number to its original value, and if we multiplied by 10 to the power of 2 in getting here, then we will have to divide by 10 to the power of 2, which is the same as multiplying by 10 to the power of negative 2. So we need to recover the original value of the number by dividing by 10 to the power of 2, which is the same as multiplying by 10 to the power of negative 2. And as it is said, we may consider a number that initially had no non-zero digit to the left or in front of the decimal point as a small number. As a rule, we may say that numbers that were initially small should be accompanied by negative powers of 10 in the end. The number of decimal places by which one number differs from the other will tell us the size of the power. So looking at this number, we have 0 point something. As long as we have 0 point something, that is a small number. The 0 point beginning the number tells us that that number is small. And I'm saying, as a rule of thumb, any such number written in standard form will be accompanied by a negative power. And we are saying the number that you accompany with the negative sign is determined by the number of decimal places that this one differs from this. It differs by 2 places of decimal, then we have a negative 2. And it is good if we can determine very early the sign that the power will have. We are required to square 0.35. Of course, that is just a matter of multiplying 0.35 by itself, or we may multiply, as we would say, two occurrences of 0.35 together. That is not the only operation in the arithmetic sentence, but that one, if we will do that without the use of a calculator, will take a more time and effort. Square is a form of multiplication. Therefore, it will take the same precedence over the subtraction operation as the product of 0.03 and 0.8. The product is not difficult. We know that 3 times 8 is equal to 24. That is what we will do. Multiply the numbers as if they do not have any place of decimal. Then ensure to give the answer the same number of decimal places as the total number of decimal places in the multiplier and the multiplicand. So we will begin by finding the square of 0.35. The least significant digit of the multiplier will be used to multiply the multiplicand. So this is the multiplier. The least significant digit will be used to multiply the multiplicand, and we will begin multiplying the multiplicand at the least significant digit, which is this one. We will then use the other digit in the multiplier to multiply the multiplicand as shown. So we say 5 5s, 25, as usual, write the 5 and carry 2 to the next column. Then we say 5 3s, 15, but do not forget this 2 that we carried from the previous column, added to the 15, the result is 17, and there is no other digit to multiply, so write down 17. That's all there is to it. We will now multiply by 3, the digit of greater significance in the number. Because of this, the first digit in the result will have the place value greater than the first digit in the first result. At this stage, one may want to include a place holding 0 before multiplying by the second number. So, before multiplying by 3, we would want to include a place holding 0, because this digit is greater in significance than this one. Therefore, after we form the product using this one, when we are about to form the product using this one, we also need to begin at a position which is greater in significance than right here. So that is why we put that placeholder 0 here, that we can multiply by 3, and the first digit will be placed right here. So 3 5s, 15. What do we do? Write 5 and carry 1. Then we say 3 3s, 9. 9 plus 1 is 10. Write 10 like that. Now, at this stage, we expect candidates to know that 3 times 35 is 105, like that. And we also expect, because we have problems like that on numerous occasions, multiplying 3 by 3.5, that is equal to 10.5. So just demonstrating some familiarity with digits should allow us to be able to just write that down without having to go through bit by bit multiplication. Finish up by adding the two results. The problem has 4 decimal places, and so will the answer. So we have, just add these. 5 plus 0 is 5, 5 plus 7 is 12, put 2 and carry 1, and then these two are added. 1 plus 1 is equal to 2, and then the other number returned as it is. Now we have 1, 2, 3, 4 places of decimal, and the answer will also have 1, 2, 3, 4 places of decimal. And I have included this 0, saying that there is no whole number part to this number. Now we need to finish the product of 0.03 and 0.8. Surely we need to do this before attempting to subtract, because multiplication takes precedence over subtraction. So what do? Each step is simple. 3 multiplied by 8 is equal to 24. So just multiply the numbers without any consideration of the decimal fraction. So just say 3 eighths 24. No problem. What do we do next? We may count the number of decimal places that are a part of the numbers that we have in the statement of the problem. So what we have here, 0.08 times 0.3. Count those decimal places. 1, 2, we have in the first one, and another one there. So we have a total of 3 decimal places. The product will therefore also have 3 places of decimal. Remember that in a whole number, the decimal point is assumed to be at the extreme right, which is where we have it right here. That is where the decimal point is assumed to be in a whole number. And we also need to have 3 places of decimal in our answer. So 1, 2, 3. Right. So we had 2 digits, and we included an additional digit, which is a 0, to complete the number of decimal places. And I imagine that we have 0 whole number. So the 0 whole number is appropriate to say that we have no whole number in this particular number. So we have a 0 right there. And after doing our square and also doing our multiplication, then we will finish up by doing our subtraction. Now we will find the difference between the numbers 0.1225 and 0.24. As usual, we will vertically align the points in the 2 numbers. So there we have the points already vertically aligned. Write the digits on both sides of the decimal point. So we have 0.024. 0.024. So on this side we'll have 024 as a matter of fact, and on the other side we'll just have 0. Then we will subtract. Although it is not a complete necessity in this particular case, we will include a place holding 0. Right. Proceed to find the difference between the 2 numbers on the next slide. Let us go straight ahead and subtract. 5 minus 0 is equal to 5. And now we are attempting to say 4 from 2 or 2 minus 4. We cannot subtract 4 from 2. We therefore remove 1 from the more significant position. Just a 1 there. And the place value of the more significant position is 10 times the value in the less significant position. Therefore, when we take 1 from here, we'll have it as 10 here, because anything taken from here will be multiplied by 10 and placed here, because this position is 10 times greater than this one. So we have, removing a 1 will be 10. So there we have it. And I usually say that this number is by no means 12. So this number is not 12 really. It is that when this 1 is removed from here, it is 10 times its value here. Therefore, what we have here is actually 10. And then we have 2, so it is 10 plus 2. But because of maybe tradition, convention, convenience, we just place the 1 here and say that because of its appearance or resemblance to 12, we are calling it 12. But really, what we should have done is the 1 that we take here. Instead of putting 1 here, we should really put 10. And then add the 2 to the 10. And then that will be 12. And 4 from 12 is 8. Much the same way that when we go over to the hour side and remove 1, when we bring it to the minute side, we do not just put a 1 like this. Why? Because it is not convenient to do so. We always bring it to the minute side as 60 minutes, and then we add the minutes that we had in the minutes section to it, and then from that we would do our subtraction. But because of its appearance, it is easy to say that 1, 2, that it is 12. So we'll say 4 from 12, when it should really be 10 here and a 2 here. So 10 plus 2 is equal to 12, and we say 4 from 12 is equal to 8. So 8 goes there, and we now are attempting to say 2 from 1. We cannot subtract 2 from 1. We therefore remove 1 from there, which is a more significant position. 0 is left there, and we have 1 there. And maybe on this occasion it looks more like 11 than anything else. And because of its appearance like 11, we say 11. And as a matter of fact, if we went the real way and said 10 plus 1 is 11. So I think that there is no ground lost by saying it is 11. But what it really is 10 plus 1. And it should really, and it really should be a 10 that we place right here instead of a 1. And we will have 10 plus 1 is equal to 11. But at any rate, this one beside the other one looks like 11, and we just accept that the entire consequence will be 11. So we do not make a big thing out of it. So 2 from 11, and that is 9. 0 from 0 is equal to 0, and we may vertically align our decimal points and 0 for our whole number is by no means redundant. We may now write the number correct to 2 decimal places. Locate the second decimal place 2 digits to the right of the decimal point. Check the digit that is next in order of significance, which is the one located to the right. The digit is 4. 4 is less than 5. Because 4 is less than 5, we do not add 1 to 3. 3 goes back. The other digits are not affected and return as they are. When rounding numbers, if the digit next in significance to the digit in question is less than 5, then 1 is not added to the digit in question. In this particular case, the digit in question is the 1 in the second decimal place, and in the second decimal place we have 3, so this is the digit in question. This one is the one next in order of significance to it, and its value is less than 5, so we do not add 1 to the digit in question. Also, it is important to note that when we are counting decimal places, we begin at the first decimal place, which is located in the first position to the right of the decimal point, and we will begin there whether or not the value of the digit is equal to 0. However, if we were counting significant figures, we will have to begin at the first non-zero digit. We will write the answer obtained on the previous slide in standard form. When writing a number in standard form, the number is written in such a way that there is only one non-zero digit in front of or to the left of the decimal point. Count the number of decimal places that will represent the difference between the original number and the number written in standard form. If we are going to standard form, what do we know? For sure that we will have only one non-zero digit to the left of the decimal point. So right here is where we expect the number is increased by 2 decimal places. The number is therefore multiplied by 100 or 10 to the power of 2. As we see right here, we have 0.03. Here we have 3.45. Surely this number is greater than this one. And how so? By 2 places of decimal. Therefore, since this is greater than this one by 2 places of decimal, then we will say that in order to get here, what we did was multiply this number by 100 or by 10 to the power of 2. Therefore, if we will return to our original value, we will have to divide by 10 to the power of 2 or 100, which is equivalent to multiplying by 10 to the power of -2. We may consider a number that initially had no non-zero digit to the left or in front of the decimal point as a small number. As a rule, we may say that numbers that are initially small should be accompanied by a negative power of 10 in the end. The number of decimal places by which one number differs from the other will tell us the size of the power. So this is a small number because it has 0 point and then the decimal. So this one is called small. So any number that has a 0 then point something is a small number. In the end, that one will have to be accompanied by a negative power of 10. So we are sure that as soon as we see this one, we know that it's a negative power, 0 point. So we are sure that the power will be negative. Then the size of the power, how many decimal places does this one differ from this one by, will tell us the number that we place right here. In this problem, we need to find the value of the given fraction. There we have it. How so quickly? The value should then be written correct to 3 decimal places and also to 3 significant figures. That we will do on the other slides. 2 decimal places and 2 significant figures. Now we may write the number correct to 3 decimal places. Locate the third decimal place beginning at the first digit to the right of the decimal point. That is where we have the first decimal place right here. And we have 1 place of decimal, 2 places of decimal, 3 decimal places. Check the digit that is next in order of significance, the one that is located to the right. The digit is 9, and of course 9 is greater than 5. But if it were 5, so any number that is greater than or equal to 5 qualifies for the addition of 1 to the digit in question. And no doubt 9 surely qualifies. So we add 1 to this one, which is also a 9. So we add 1 to 9, and what happens? 9 plus 1 is equal to 10. So we put the 0 down and carry 1. So 9 plus 1 is 10. Write 0 and carry 1 to the next position, where we will say what? 3 plus 1 is equal to 4. So 9 plus 1, 0, carry 1. 1 plus 3 is equal to 4. The digits to the left are not affected, and they return as they are. The trailing 0 cannot be discarded. Why? Because we have 1.040. This 0 does not affect the size of the number. So why can't we eliminate this 0? The trailing 0 cannot be discarded, although it is not contributing to the value of the number. It is maintaining the required number of decimal places. So it is maintaining the required number of decimal places we have here. Now we may write the number correct to 3 decimal places. Therefore, in the end, we should have our number depicted with 3 decimal places, no less. So even though this 0 is not contributing in any way to the value of the number, it is contributing to the required number of decimal places, which is 3. Now we may write the number correct to 3 significant figures. Locate the third digit in order of significance by counting from the left, where we will find the most significant digit. So locate the third digit in order of significance by counting from the left, and there we will find the most significant digit at the left. 1, 2, 3. 1, 1, 2, 3. Check the digit that is next in order of significance, the one located to the right. The digit is 9, which is greater than or equal to 5. We add 1 to 3. So 3 plus 1 is 4. Nothing to carry on this occasion. The other digits to the left are not affected and return as they are. One danger in solving this problem may be caused by candidates not counting the 0 between 1 and 3 as a significant figure. It is a significant digit, being indispensable because it is occupying a significant position. So this 0, we cannot eliminate it because its existence or presence here helps to modify the place values that we have here, to the extent that if this one were not present, then this will be 3/10. But because of its existence, this is 3/100. Therefore, this is a significant digit, although its value is 0. Its place value is significant.